Welcome, this is Information Service Engineering, lecture number 3, Linked Data Engineering. This is the last part of the first lecture on linked data engineering. In this part of the lecture, we will talk about logical inferences, which are possible based on RDF and RDFS. To begin with, we again have to pose ourselves the question, where does the semantics come from? How much knowledge is there in an RDFS representation that you see here? So we already know that the names that we use as URIs usually carry, of course, here in that examples, human readable information, but of course the machine doesn't see that. So therefore, the semantics comes from somewhere else. The semantics simply is defined for an RDFS ontology in terms of its properties and its values. And the properties, they connect entities with each other, and the values, of course, they give an object a specific value that again characterizes a specific property of the entity we are talking about. However, we know that there is specific vocabulary used. This vocabulary comes from RDF and RDFS. And this also carries a specific meaning, which means there the semantics is formally specified. It's clear what it means. For example, that an entity is of type of a class. This means that the entity is an element of that class. By that, we have a so-called formal semantics. And this is something which distinguishes RDF and RDFS from other kind of data definition languages. So RDFS is based on formal semantics, which enables RDFS to draw valid and sound logical inferences. With other kind of data definition languages, like for example with UML, you are not allowed to draw sound logical inferences, which means you cannot simply deduce new knowledge which is not explicitly given from the existing knowledge. With RDF and RDFS, this is possible. So let's have a look how these kind of models look like. So we have here a small example. Again, we have Pluto is a dwarf planet, and a dwarf planet is a subclass of a celestial body. And we have artificial satellite of, which is a sub-property of satellite of. This RDFS model can simply be mapped to a set-theoretic model. Look at the set-theoretic model in the blue box over there, which says that Pluto is an element of the class dwarf planet. And it also states that the class dwarf planet is a subclass of the class celestial body, as well as the artificial satellite of is a subclass of satellite of. This can simply be achieved by representing these properties by the elements of domain and range which are connected by the property. This is called the property extension, and then this can be treated like a class. And then you have here a set-based model which defines the so-called model theoretic semantics of RDFS. And based on that, you can draw conclusions, sound mathematical conclusions. We will have a few examples on that. Okay, so which conclusions can we draw with RDFS? Let's have a look at this small example here. Again, we have Sputnik 1, which is an artificial satellite of Earth, and we say that Sputnik 1 is an artificial satellite, which is a subclass of satellite. By taking into account that here we have first a type relation, which means Sputnik 1 is an element of the class artificial satellite, and by having a subclass relation between the two classes artificial satellite and satellite, we can make a simple deduction, which in the end will tell us that Sputnik 1 also is of type satellite. And this deduction can be drawn simply by the following rule that you see here, that of course is part of the semantics of RDFS, which states that for all individuals I and all classes C sub 1 and C sub 2, it holds that if you have a triple which connects an entity I and says I is of type class 1 and class 1 is a subclass of class 2, then it follows that I also is of type C sub 2. So this is a simple rule which states what is the semantic exactly of the type and the subclass relation and what kind of inferences am I allowed to draw from exactly that property. So this is clearly simple. Let's look at another example. Here we have Pluto, and Pluto, we say it's also a satellite of something without exactly specifying what it is. And then you have also the property definition from satellite of, and it says that there is a specific domain and range. In both cases, this is celestial body, and it states that satellite of is of type property. Okay, what we can deduce is the following class membership simply from knowing that satellite of has a specific domain and a specific range. We can draw conclusions about the entities which are linked by exactly that property. So for example, we can say that Pluto must be of type celestial body. And this comes from the following rule, which says that for all individuals I sub 1 and I sub 2 and all classes C sub 1 and C sub 2 and all properties P, it holds that if I have a triple in the following form, that individual I1 is connected via property P to individual 2, and for this property I have a specific domain which is class 1 and I have a specific range which is class 2, then it holds that I sub 1 must be a member of class C sub 1 and I sub 2 must be a member of class C sub 2. So therefore I can draw the conclusion that Pluto is of type celestial body, as well as the other thing, which is here in our case a blank node, must be nevertheless of type celestial body, because only this is allowed according to the property definition that we have here. This is quite nice, isn't it? And we can even do more. So here we have a more complex example. Again, Sputnik 1 is an artificial satellite of Earth. We have the property artificial satellite of defined with its domain and range, and we say this is a subproperty of satellite of, which again has domain and range celestial body. From that, I can draw the conclusion that I can deduce a completely new fact, which states that Sputnik 1 is a satellite of Earth. So not only an artificial satellite, but also a satellite of. So this comes from the subproperty relation we have here. And the deduction is drawn from the following rule that states that for all individuals I sub 1 and I sub 2 and all properties P sub 1 and P sub 2, it holds that if I consider a triple like I sub 1, property 1, I sub 2, and we say that property sub 1 is a subproperty of property P sub 2, then it holds that I sub 1 also is connected to I sub 2 via this new property, the superproperty P sub 2. So this is simply the same fact that I was explaining you expressed here in first order logic. And based on first order logic, of course, if I use this as a formal mathematical model, with first order logic, of course, I can draw conclusions. And this is what makes exactly a model based on ontologies, which are based on a formal mathematical model, superior to any other kind of data definition language, which lacks exactly this mapping to a formal logic. Okay, so I told you this is the first lecture that we have on linked data engineering, and now we have come to an end of this first lecture, and we have talked about identification of things on the linked data web, on the semantic web with the help of URIs. We have talked about the resource description format. We have talked about model building with RDFS, but this is only the first part of the entire framework, and there is much more. So if we want to build more complex applications, more complex solutions like the fellow on that interesting slide here, then please visit Linked Data Engineering 2, which will take place here next week.